Welcome to this lecture series in number theory. We are starting a new module in which we will discuss Euler's totient function and Euler's generalization of the Fermat's little theorem. The main ingredient that we will need is, well, all the general theory about G series, etc. But crucially, the Chinese remainder theorem, and specifically this version of it. There is a version which says that you can solve congruences simultaneously if the divisors are relatively prime. This, that. But we recasted that in a certain way. So if m and n are two positive integers which are relatively prime, then we can define this map from the set of all the remainders modulo mn to the set of all the remainders modulo n times the set of all the remainders modulo n. And this map is very natural. It takes just a remainder or whatever, an integer, to the pair of the possible remainders. So I don't want to spend too much time on it. I'm sure you recall. And the Chinese remainder theorem says that this is a bijection. Okay, so with that, let us proceed. So let's define the totient function. I don't know where the name comes from, but it is standard. So define a function from naturals to naturals as the name of the function is phi. In literature, you will see this kind of phi, but I have gotten used to this kind of phi. It's just a different phi. So phi of n is the number of those natural numbers which are not exceeding n and which are relatively prime to n. So in set theoretic language, it is the size of the set. It's those natural numbers k which do not exceed n and which are relatively prime to n. Okay, that's the definition. It's a very nice definition. Note that this range is not some artificial thing. That's because the relative primality of some integer modulo n only depends upon the remainder class of k modulo n. In other words, if k and l are same modulo n, then either both of them will be relatively prime to n or neither will be. So therefore, this is sort of the range of all possible remainders, except that when we say remainders, we usually say 0. I mean, we include 0 as a remainder. We don't call n as a remainder. But once you look at the remainder class, n is same as 0. So I hope you're able to see that this is not some artificial range that we just decided. Okay. So we have this definition. And before I make a small note, I need to discuss some examples. So let's write down the values of this function phi for at least the first n integers. So phi of 1 is 1. That should be clear immediately. Phi of 2 is also 1. Because what are all the natural numbers which are between 1 and 2? They are these. And the last one is certainly not relatively prime to 2. So there is only one thing in the set whose size we needed to record. Okay, similarly, phi of 3 is 2 because everything smaller than 3 and any natural number smaller than 3 is relatively prime to 3. So that's 2, and this is also 2. Phi of 4 is 2 because these are the 4 things that we needed to worry about. 2 and 4 are not relatively prime, so only 1 and 3 are. This is phi of 5 is 4 simply because 5 is a prime. 1, 2, 3 and 4 will be relatively prime to 5. 5 certainly won't be. This is, let's see what this is. So 6 is not relatively prime, 4 is not, 2 is not, and 3 is also not. So this is 2. 5, 7 is 6. And this one will be all the odd numbers, which is 4. This one, all the things which are not divisible by 3, right? So that would be, I think, 6. And phi 10 will be, let's do phi 10 properly. So this is gone, all the evens are gone anyway, and 5 is also gone, and everything else that remains is there. So you can verify this is equal to 4. Okay, more generally, or at least a general class of examples, if p is a prime, then what are the things in the range 1 up to p which are relatively prime to p? Well, everything less than p. So this is p minus 1, if p is a prime. Should be clear. More generally, if you have a prime power, then what are all the things in this range which are relatively prime to p power n? Well, since p is a prime, this is equivalent to asking all the things in this range which are relatively prime to p, which again, since p is a prime, is equivalent to asking those things which are not divisible by p. But in this range, how many things are not divisible by p? It's the total number of things minus those things which are divisible by p, and that number is this. So this turns out to be the following expression. So for prime powers, we can immediately calculate, and you can verify for the prime powers that we did calculate that this expression is actually correct. Before we proceed, I want to make one comment. If we have a natural number n, then phi of n can also be written this way. What is the difference? Previously the range was 1 up to n, this time the range is 0 up to n minus 1. As I said, the relative primality only depends upon the remainder class and not the number itself, and that is all that we have done. Even if you shift everything by 1, it doesn't change anything. So I hope this point is clear. If it is not clear, think about it, it will be clear. So with that, let us move on. Yeah, so what is the point? Why are we, this is what I'm calling the main observation. Why are we doing this? We are doing it to prove something which will allow us to calculate the value of phi for any input. Right now, we have seen that we can calculate phi for primes and prime powers. We have a sort of a formula for it. But we do not have a general formula or a general algorithm to calculate phi except the brute force. You just list out all the things between 1 and n and cancel out all the things which are not relatively prime, blah, blah, blah. But we will at least give something better than that. And for that purpose, we have this lemma, which has its own importance. So what does this lemma say? First of all, we have this Chinese remainder theorem. This is the bijection that is furnished by the Chinese remainder theorem. We are assuming that m and n are relatively prime. What we are saying is that this map f, what was that map f? Let's just write it down. It takes x to this pair. So this was the map by the Chinese remainder theorem, which is a bijection, we know it. What we are saying is that if you restrict that map to this set, what is this set? It is all the things here which are relatively prime to mn. So if you restrict that map to this set, we are saying what you will see as the image is this set, which is what set? The first thing is all the things which are relatively prime to m contained over here, and the second thing is the set of all the things which are relatively prime to n contained over here. So in particular, this is a subset of that guy, this is a subset of that guy, and this is a subset of that guy. Okay? Right, and we are just saying that this bijection restricts to that bijection. And to do this, we need to first prove that if we pick something from here, it will land here. It will land in the cross product here. And secondly, if we pick something from here, it is the image of something here. Okay? And it's not at all hard because we know the basic properties of GCDs. So for the first direction, suppose we pick something in the first set, and let me give it some notation because otherwise there will be too much writing. So this we will call as, I don't know how to notate it, but I will call it as, let's say, let me call this as SMN. This I will call as SM. And this I will call as SN. So if we pick something from SMN, want to show that x mod m is in SM and x mod n is in SN, which is to say that this is equivalent to saying x is relatively prime to m and x is also relatively prime to n, but that is clear because this means that x is relatively prime to both m and n. Right? What does this mean? This means that x is relatively prime to both m and n, and hence this clearly follows. So this part is clear. I'm not writing any more details. Let's do the other direction. So for the other direction, pick something from the right hand side, meaning pick a pair from this cross product. We want to show that there is something here whose image is this guy, but since this was a bijection, there is something here whose image is this guy, right? In particular, anything here is also in the target of our map F. So we just need to show that if X is the element here whose image is this guy, then X actually lies here. So say, before we proceed, want to show that there exists X in Smn such that f of X is a comma b, but since f is a bijection, there exists X in all the possible remainders modulo Mn such that f of X is a comma b. But what is f of X? X mod m comma x mod n. So we know that there is an X here such that a is x mod m and b is x mod n, right? This equation just tells us that x mod m is a and x mod n is b. Now what that means is that X is relatively prime to m. So thus, maybe I'll write every step. So this implies that x mod m is a and x mod n is b, which, since a is relatively prime to m, right? A is relatively prime to m, hence so is x, and b is relatively prime to n, hence so is x. So the GCD of X with m and n is 1. So we deduce this, but now by our basic understanding of GCDs, by the clubbing property or whatever, this implies that the GCD of X with Mn is 1. If it is 1 with both of these two things, then also with the product of M and N it will be 1. And that is exactly what we wanted to do. We wanted to show that X actually lies in Smn, which was equivalent to showing that the GCD of X with Mn is 1. So I haven't written it in a very formal way or anything, but I'm sure you are able to complete this proof. It's nothing, it's just the basic properties of GCDs coupled with the Chinese remainder theorem that we already know. It's not a new idea in any way. Okay, after this observation, we see that the size of this set is same as the product of the sizes of these two sets. But what is the size of this set? The size of this set is phi mn, and the size of that is phi m times the size of that set, which is phi n. So we have shown that if m and n are relatively prime, then phi mn is the product of phi m and phi n, and that is what I've recorded here. You pick any two relatively prime integers a and b. In the previous slide it was m and n. If you pick any two relatively prime natural numbers a and b, then phi of ab is equal to phi a times phi b. Right? So we have justified it. And this helps us compute the value of phi in principle for any natural number. So here is the general theorem. You pick any natural number at least 2 so that you can write it as the product of prime powers. Then phi of n would be phi of p1 to the power k1. So yeah, these are distinct primes. So this is the prime factorization of n. These are distinct primes. I haven't written it, but they are. Okay, so this times the dot 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 phi of pr to the power kr, right? Immediately by our previous proposition, because these are distinct primes, these things are pairwise relatively prime. So you repeatedly apply the multiplicative property. The previous property is called the multiplicative property of phi. I did not mention it, but I wrote it in the heading there. Whatever, so applying that property, we get that phi n is equal to this product. But what is this product? For prime powers, we had already calculated this thing. So this is p1 to the power k1 times 1 minus 1 upon p1 times dot 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 PR to the power KR times 1 minus 1 upon PR, which, if we do some shuffling, we get this. But what is the first term? The first term is n itself. So if you know the set of primes that divide n, then phi of n is n times this particular number that depends only on the set of primes that divide n. Okay, so that's a nice formula, and well, it is a formula but also not really a formula in the following sense. I have written it in double quotes. It is not a formula because finding this factorization is difficult. In fact, it is a big open problem in number theory or computer science that factorization is a hard problem, in the sense it is computationally hard. There is no good algorithm to quickly compute the prime factorization of any natural number. This is a hard problem, or believed to be a hard problem. And let's just do this example, and that will be it. So what is phi of 360? Well, what is 360? So 360 is 12 times 30, which is 4 times 3 into 3 times 2 into, yeah, that's what it is, which is equal to 2 cube 3 square times 5. So I've computed the prime factorization, and hence phi of 360 is this number, which is 360 times 1 minus 1 upon 2, 1 minus 1 upon 3, 1 minus 1 upon 5, which is equal to that, and hence this is same as 12 into 8, which is 96. So it helps. For small numbers, you can quickly compute the prime factorization. So it helps even for some computational purposes. What is more important here is the theoretical aspect of it. Even though this is not going to help you compute the value of phi very quickly, it has theoretical importance. As you can see, if you want to prove something about this number, you should be able to believe that this particular this particular formula may help out, right? So I will give a lot of exercises in the next lecture, which will help you appreciate this point more. And yeah, with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.